Okay, good afternoon, everyone. I'm Paul Darsh, the Director of Marketing here at John Brooks. Thank you for attending today. And if you've joined us before for one of our webinars, then we're really happy that you've returned. If this is your first time, then welcome. Either way, we hope that you'll find today's topic interesting and useful. This is our third webinar in our centrifugal pump series and follows our first one on hydraulic considerations when selecting a centrifugal pump. And then the second one that was a few weeks ago was on the analysis of multiple centrifugal pumps in piping networks. And if you missed those, or if you'd like to see them again, we will send you a link of their recordings to all the attendees today so that you can review them at your leisure. Today's presentation will also be recorded and its link will be sent to you as well. Today we're having an in-depth discussion on pump cavitation, and as usual for this series, our main presenter is Stefan Fediw. Steph is one of our technical representatives in our pump division here at John Brooks, and he has over 25 years of experience in fluid handling industry with several pump manufacturers and distributors. And Steph is joined again today by our guest panelist, Chris Chapman. Chris is currently our outside technical rep in Southwestern Ontario. And prior to joining John Brooks, he has held different roles at Gorman Rupp in engineering, manufacturing, and technical sales. As with previous webinars, your mics will be muted by default for the duration of the presentation. Please use the Q&A icon on the Zoom meeting control bar on your screen to submit any questions you might have. Steph and Chris will be presenting for about 40-45 minutes or so, and we'll be monitoring the Q&A box. So we may decide to answer some questions as we're going along, and then others may be at the end of the presentation. We want to respect your time commitment and the 1 hour schedule. So if there are any extra questions that we don't get to, we'll make sure they're addressed by email as a follow-up. And again, thank you for attending. And with that, I'll turn things over to Steph and Chris.
Great. Thanks, Paul. And thanks to everyone for attending again. This is a lot of fun. I do enjoy this. And thanks, Chris, for also attending, for helping me out here.
Welcome.
First thing is who John Brooks is. We were established in 1938. We're a privately held Canadian company. And there's over 200 of us, friendly people, I like to think, across Canada. And we are a full service national supplier of pumps, filtration, spray nozzles, custom skid packages, specialized valves, and pressure vessels. Okay, so what are we going to cover today is we're going to talk about some centrifugal pumps and impellers, then cavitation, suction cavitation, recirculation cavitation, discharge cavitation, and then at the end, we will be giving out in the next day or so a personalized cavitation webinar trainee certificate. Now, just a little story about these. We normally give these out when we present in person. And up here on the top side is where we have a little impeller that shows all the different damage due to cavitation. And that's usually a little impeller physically painted. Unfortunately, in this day and age, we can't do that. So we're going to give out a PowerPoint slide of this 3D model, which you'll be able to rotate and take a look at the cavitation in the privacy of your own office. So that'll be sent out to you in a day or so after the presentation. We'll also be giving away a few e-cards here. We're going to have a little bit of competition, ask a few questions, and we'll send those out to you as well. So let's get started. Today, we're going to really concentrate on centrifugal pumps and cavitation. Obviously, positive displacement pumps cavitate as well, and we'll take that up on May 28th in 2 weeks' time. So how do impellers move fluid? Well, if we surround an impeller, start it to spin and surround an impeller with fluid, by centrifugal action, not centrifugal force, because in my opinion, centrifugal force doesn't exist. It's only centrifugal action. We're going to throw the liquid outward, and what we're going to leave behind is a void or a low pressure zone. And that's always a good thing for any pump, because if we now put this pump in an application, and let's say it's just on a lift for argument's sake, what we're going to do is we're going to set up a differential in pressure. Again, positive displacement or centrifugal. All pumps work this way. They generate a low pressure, an atmospheric pressure, tank pressure, system pressure, whatever, pushes the fluid into the pump. Again, pumps don't suck. We cannot pull on fluid. It has no tensile strength. Different types of radial flow impellers. First one is the enclosed over here. And the reason why we're calling it enclosed impeller is because it has a front shroud and it has a back shroud. And when looking at it head on, we really can't see the impeller vanes. Second is a semi-open two-vane impeller. And we call it semi-open because it has no front shroud. It only has a back shroud, so we can actually see the impeller vanes. It's open. And finally, semi-open multi-vane impeller. This one, just like the semi-open two-vane, just more vanes. So what happens while a pump is pumping? Well, it's generating this low pressure at the eye, and it's accelerating and energizing the fluid outward and developing a high pressure. Well, this could become a mixer if we're not careful. If we don't keep a close tolerance between these high pressures and low pressures, this throttling system, then we're just going to get a mixer. So with a semi-open impeller, we have to add what's called a wear plate. And this is most semi-open impellers, we have this. And this wear plate will fit tightly up against the face of the impeller and ensure that the liquid does not sneak back to the low pressure zone. And we'll take a look at that right here. This just happens to be a trash pump. The way that this wear plate is attached to the pump is always a little bit different in all pumps, but in this case, it would be attached to the clean out cover or the trash cover right there. And the impeller obviously is inside the pump, and they would mate together to make a nice tight fit. So essentially, when this gap opens up, what we're going to get is recirculation. High pressure from the tips of the impeller vane will push the liquid not out the pump casing itself, but to recirculate into the suction. And that's not a good thing. We have a pump because we want to move liquid. We don't want to mix the liquid. So this becomes very inefficient. And if we were to look at a pump curve here, just a generic pump curve of a new pump, flow on the bottom, head on the top. Obviously, from our other two webinars, we know where the pump curve crosses the system curve is where the pump should operate. Well, if we start to get these internal tolerances opened up, this new pump becomes a worn pump. And essentially, it's like running this pump slower or trimming the impeller down. We're not performing, we're not getting the flow or head out of this pump that we would expect. So if you had gauges on this pump, you'd see the gauges drop off, or you'd see the flow rate if you had a flow meter. Or quite simply, if you didn't have either of those, if it took you 10 minutes to empty a tank, it might take you now 15 minutes because you're not pumping as much. So it's really important that we keep these tolerances nice and tight. So when these tolerances open up, because the wear plate is wearing, what we can do is usually there's some external adjustment. In this case, it would be from the cover plate itself. We'd push that cover plate a little closer. And we could keep doing this over and over again until we wore that wear plate thin. And then we'd probably have to replace that wear plate. And maybe by that time, we'd have to replace the impeller as well. So now let's look at an enclosed impeller. How do we keep these tolerances in an enclosed impeller? Well, it's a little bit different. Let's first take a look at what an enclosed impeller pump looks like. There's the enclosed impeller, and here is the pump volute. If you look inside, there's no wear plate here. That pump impeller, the front shroud, sits right up against, but doesn't touch, hopefully, the front of that volute. Now, if we put these back together again and see how that volute actually interplays with the impeller, we'll see here, that's the cross-sectional view, that blue cross-sectional view of where the volute actually sits. And if we take a close-up look, this is a brand new pump, nice tight tolerances. And as the pump pumps, depending on how much pressure is being developed at the outer vanes, will depend on how much recirculation we would get through the front side of this impeller and volute. Now, obviously, when this pump is new, we're not going to get a whole lot of recirculation. But as this wears, we're going to open up the tolerances and we're going to get more and more wear. And unfortunately, again, that warm pump is going to start to drop in performance. And we don't want that. We obviously want to get this back in play. Well, what do we do here? How are we going to replace this? It's going to get expensive to replace a volute every time it wears. So what we do is we have something called a wear ring. But before we look at that, let's look at the actual wear component here. All this flow is going from the outer high pressure portion of the impeller back to suction. And it first has to go through the face of the impeller and also the face of the volute itself. If you can imagine, that is quite a large area, quite a large surface area. So this flow really doesn't wear away a lot, this location, because it's such a large area. Where the location is that's really going to see the wear and tear is going to be around this front area right here. All that wear, all that flow has to go over that small area. So therefore increasing the wear. And again, this is really applicable when we're pumping maybe something that's not quite clean, not a clean water, maybe something with a bit of silt or sand or slurry inside of it. So what we can do is we can insert what's called a replaceable wear ring, okay? And that's now going to be the sacrificial component that will wear instead of an expensive case. So let's take a look at where that would be. That would be usually pressed into the volute itself. It's just a press fit that gets pressed in. And again, this is the difference between a less expensive pump and a more expensive or valuable pump. It all depends what you're pumping. And once we have that, once we've worn that away, we turn the volute around, we can push that wear ring out. Just to go back one, sometimes with very abrasive material, we sometimes will also want to put a wear ring around the case as well, because there's going to be some high velocities around here. So there's a few ways that we can keep a pump up and going. Now we are going to get to cavitation here because this is all related. Let's just take a look at this cut sheet here on semi-open impellers, two-vane and multi-vane. Well, they both can handle solids to some extent. They both have a semi-open impeller, so we can get to the blockages if they happen. Obviously, a two-vane impeller is easier to unblock, or it won't even block to begin with because there's a lot more space between those impeller vanes. Whereas a multi-vane impeller, there's more vanes and they're closer together, therefore the chance of blocking is much greater. Efficiency. Well, efficiency on a multi-vane is always going to be more than a single or than a two-vane impeller, all things being equal. I like to think of a vane as like parents and the liquid as being children. The more parents you have around, the better the children behave. That's usually the case anyway. This is the same thing here. The more impeller vanes that you have to influence that liquid as it flows through the impeller, the better it is for efficiency. Right here, we've got a lot of space between these two impeller vanes. Therefore, this liquid tends to not be influenced as much by these impeller vanes, and therefore it tends to swirl and do all sorts of things that isn't pumping, that isn't moving the liquid itself, and therefore the efficiency tends to drop. Whereas a multi-vane impeller, more vanes, as a general rule, we get more efficiency. Now, there's something that we're going to talk about a little bit later on, and we'll definitely give a card away shortly here, is there's something here that has to do with every impeller that mimics efficiency. Here, as efficiency drops, then this secret behind this box also drops. And as efficiency increases, this secret portion of the pump also increases. So we'll talk about that. Radial flow impellers, enclosed impeller, solid handling. Well, we've got two here. We've got two enclosed impellers here. We've got to be careful. Many of us might think this is an enclosed impeller. Well, it is. And is it efficient on water? Sure. And is it good at solid handling? Not really, because we can't see the impeller vanes, and therefore if anything ever gets clogged, we won't be able to clean it out. But down below is also a enclosed impeller. It just happens to be a mixed flow impeller. So right here is actually a front shroud. So I would say, and do you agree with me, Chris, that this actually could handle solids quite well because you can access the impeller.
Yeah, large openings, large suction inlets.
Correct. So therefore, just be careful when we say enclosed impellers and open impellers. There's always a little bit of a nuance there. And also with these type of impellers, we've always got that ability to, we don't have necessarily a wear ring, a wear plate, but we've got wear rings. So, you know, they can be put on abrasive liquids as well. Just got to be careful. There's no hard and fast rules. The final impeller we're going to talk about is the Vortex impeller. And just show a quick video here. Let's hope it works here. So this is just one of those, I think it's called a Dirt Devil. Essentially, it's an impeller. Sorry, not an impeller, a tornado. And essentially what we're doing is we are vacuuming up, creating a low pressure zone by vacuuming up the product that's on the surface of the ground. And there's an impeller that does the same thing. And this is called a vortex or recessed impeller. And this type of impeller has special wings that create a drag on the fluid in front of it. And it tends to induce, and it tries to induce a tornado. And this is an example of it right here. This is the impeller. Here's the suction and here's the discharge. And here's this great big bowl, a great big space right here. And as this impeller spins, it induces a vortex or a tornado, which would be a low pressure at the eye of that tornado. And it will, let me just play the video here. It will bring in the solids. The solids are obviously still going to get pushed into this low pressure zone and expel the solids. And what's cool about this kind of impeller is that it can handle large solids at low flows because the impeller is rather small and therefore it can operate in low flows. Unfortunately, if we had to have an impeller that could handle, let's say, a 3-inch solid, a baseball, it would have to be a big impeller. And therefore, big impellers don't like giving out small flows. So again, in this case, this is for relatively small flows, but very large solids. Now, Chris, what do you think the negative is here? There's always a negative.
I suspect that it's the efficiency would be a problem with this pump.
Yeah, you're right. Efficiency is going to be about in that 30 to 40% range. So nothing's free in life. And again, this is just another way of moving fluids. Not all fluids are clean water. Okay, so let's now get into pump cavitation because we'll go back to what we spoke about there in a second. First card giveaway. So what we'll do is the first person that can type in the answer to this question, and I'll play this video. This is water at 23 degrees Celsius. Let me play it. First person to tell me why this liquid appears to be boiling at 23 degrees Celsius. And let me know, Chris, when we've got 1 or 2 in here. So why is this boiling? Why is water boiling at 23 degrees Celsius? How do we...
Certainly people are quick at answering. We're up to 20 answers already. So I'm not sure how many Timmy's cards you've got in your back pocket there, Steph, but we shall. Unfortunately, the first person was a John Brooks employee, so he does not get the Timmy's card. Okay, good.
Well, I'll answer it anyway, and then we'll sift through it later on when we get off the air here. But essentially what's happened is we've got a vacuum pump, and this whole container here is a glass container, and we keep evacuating the atmospheric pressure from this container. So this liquid is boiling, or this water is boiling, because there's no atmospheric pressure to keep this liquid liquid. We need atmospheric pressure to keep liquid liquid. So let's... we'll go on about that in a second, but let's first of all talk about cavitation. My pump is noisy, why? And there's a very common question. I know we've had that question many times, right, Chris?
Mm-hmm.
If we can set aside that it's not because of a mechanical issue, it's not because of a bad bearing or an impeller that's out of balance or unfortunately some kind of blockage, then if it's not a mechanical noise, it's probably cavitation. Cavitation is the #1 cause of hydraulic noise. Okay, so if you've got a noisy pump and we've done the mill writing thing and we know that it's not a mechanical problem, then we're probably going to start leaning towards cavitation. So what is cavitation? Cavitation is the vaporization or the boiling of a liquid and then the implosive return of the vapor back to liquid. It is not caused by air bubbles. And I say that because a lot of people do think it's air bubbles, and it definitely looks like air bubbles. Chris and I and several of us take around the glass face pump. And when we get that thing cavitating, you would swear that the cavitation bubbles are air, but they're definitely not. Air causes other problems. So here's a cavitation. Here's a vapor bubble on the left-hand side. And that vapor bubble is obviously vapor. And this is the progress of that vapor bubble turning back into liquid as it goes from left to right. And the reason why it's turning back into liquid is because it's going into a high pressure zone. And therefore, it's becoming liquid again. Now, it does not do this nice and evenly. It does not collapse on itself evenly to a nice little pop. What happens is it sends down a pressure spike right at the very end of its collapse. And that pressure spike is between 200,000 to 300,000 PSI. Now, I don't know about you, Chris, but I don't know of too many materials that can handle 200,000 to 300,000 PSI. It's pretty aggressive. So here is actually a vapor bubble that is collapsing back into liquid. So we're going to start to pressurize it, and it's going to happen pretty quickly. So just watch. So here's the vapor bubble, and now it's starting to collapse back into liquid. And right here is that pressure spike, 200,000 to 300,000 PSI right there. And you're going to hear a pop or a bang or a gravelly noise. And it's not that you're pumping gravel. It's not that you're pumping marbles. It's because these vapor bubbles have formed for whatever reason. We'll talk about that, but then have entered into a high pressure zone and collapsed. And we get this severe hammer, essentially 200,000 to 300,000 PSI. So let's go into outer space for a second. And let's take some water into outer space. Now let's assume the water will stay liquid. I know it's going to be cold out there, but let's assume it is. The first thing that's going to happen to that water, as long as it's liquid, is it's going to vaporize. It's going to boil because there's no atmospheric pressure out there to keep it liquid. It takes atmospheric pressure or some kind of pressure to keep it liquid. And this is where this vapor chart comes into place. It comes into play. If I've got liquid out in outer space, how much pressure do I need to keep on that liquid in order to keep it from vaporizing? Well, let's say it's 38 degrees Celsius or 100 degrees C in this particular application. I would need to keep at least 0.949, or let's call it 1 PSI on that liquid in order to ensure that that liquid does not vaporize. If I put anything less than 0.949 PSI on this liquid, on this water, it will vaporize. Again, if I go down to the bottom there, 99 degrees Celsius. At 99 degrees Celsius, I need to keep about 14 PSI on water or else it will boil. And that makes sense because on Earth, where atmospheric pressure is 101.3 kilopascals or about 14.7 PSI, at 100 degrees Celsius, I overcome that pressure, that atmospheric pressure, and I boil that fluid. So let's keep that in mind as we go back to Earth now. And let's take a look at a pump itself. Let's get it spinning. As we said, the way any pump generates flow is that it creates somewhat of a lower pressure at the eye, and then atmospheric pressure, tank pressure, system pressure pushes the fluid into the pump. Well, what happens if that vacuum becomes very, very low? Well, what we're going to do is, possibly, we could vaporize or boil that fluid at room temperature because we've pulled such a vacuum on that liquid. Again, remember that video that the first Tim Hortons card was given out for. We saw liquid water boiling at 23 degrees Celsius. And the only reason it was boiling at that temperature was because we had a vacuum being pulled on it. Same thing here. So let's see why the fluid boils to begin with. Let's make sure that we don't have that fluid boil. So we're going to have to do some calculations. But before we do that, let me ask a question here. Let me change my pointer. And all you have to answer is either 1, 2, or 3. And what we'll do is, you don't have to be the first person to answer. We'll take a look at them all and we'll randomly pick one of the answers, one of the correct answers later on. And the question is, when the pumps are operating, these two pumps here, one's flooded, one's on a lift, where is the lowest pressure located? Where's the lowest vacuum? Where's the lowest pressure? 1, the fluid surface, 2, the suction inlet, or 3, the impeller center. 1, 2, or 3. I'll give you a few minutes just to kind of, a few seconds to take a look at that. Where is the lowest pressure? Fluid surface, the suction inlets, or the impeller center? We're obviously getting there, Chris.
We are, yes, the answers are rushing in. We're up to about 20 answers right now, 21. So yeah, they are flooding in.
Okay, we'll have to root through those later on and see which ones are right, and then we'll pick a few and send some cards out. So the right answer is going to be the eye of the impeller. That's what's really generating this flow on the suction side. So it better be the low pressure zone, okay? So what we want to do now is we want to go through a calculation that's involving what is the actual vacuum draw at the eye of that impeller. I'm going to look first at this flooded pump, okay? So what's the first thing that's acting on this liquid? Well, atmospheric pressure is acting on this liquid. Great. Then what is the pressure at the suction, middle of the suction of the pump? Well, it's going to be the atmospheric pressure plus the weight of the fluid, or the pressure of the fluid, the static head of the fluid that's on top of this distance from here to here. What's on top of the eye of the suction. Okay, that's good. That's all positive. That's all going to keep that liquid. But now we have to start taking things away. And the first thing we take away is friction. Obviously, through the suction line, as we start to pump fluid, there's going to be some resistance to friction. Again, we all know on a system curve, there's only 2 things that make up a system curve and what pumps have to pump against, and that is friction and static head. Well, in this case, the static head is positive. We just have to pump against the friction. And the second thing is the vapor pressure. We've got to make sure that we include the vapor pressure. We want to keep a margin that we keep on top of the fluid, this vapor pressure. And again, just as a reminder, that vapor pressure can be read from a chart over here. And if we're not pumping water, then there's a vapor pressure chart for gasoline, for ethanol, for whatever you can ever think of, there's a vapor pressure chart for. So that all together makes up what's called net positive suction head available, or NPSH. And all what that means is, what is the absolute pressure of the fluid as it enters the flange of the pump? It hasn't entered the pump yet, but it's right at the flange of the pump. What is the absolute pressure? Remember, absolute pressure, there's no negatives. It's just how much more above zero absolute do we have here? And also with the vapor pressure taken away. That's all what NPSH available means. So we've got NPSH. That's our driving force. Now we're going to start taking things away. NPSHR, net positive suction head required. What is that? Well, let's take the mystery out of it. All what net positive suction head required are the losses from the flange of the pump to the eye of the impeller. That's all you have to think about this. That's all you have to think this is, and it won't steer you wrong. NPSHR is the losses from the suction flange to the eye of the impeller, internal, because there are internal losses in a pump. So this is where we're going to start to look at this map again, this page that we're looking at before. Remember, on our 2-vane impeller, we had very, very low efficiencies. Well, guess what? Our NPSH is also low. That's a good thing. On our semi-open multi-vane impeller, our efficiencies might have been high, might have been low. Well, if they start to creep up on the high side, well, so will the losses inside that pump. They are definitely in step with each other.
Steph, I've got a question that might be worth covering there. I don't know whether it's going to come up or not.
Yes.
Is that required value a calculated value?
No. An NPSH required can only be given to you by the pump manufacturer, because they know, they've done the test. Essentially, they do a test that brings out what those losses are as we pump more and more fluid through the pump. And we'll look at that NPSH-R curve in a second. So we're just going to open this up to the next question here. when I click this box, what's going to show here as the efficiency of the water, as the efficiency of this pump increases or decreases, what will follow? And I've said it before in the answer, and I'm going to say it again. It's going to be NPSHR, okay? So let's take a look why, because it does seem to be counterintuitive that a high efficient impeller has really poor efficiency as far as losses on the suction side, the internal losses. So let's take a look at why that is. If we think about the flow through an impeller, an enclosed impeller, very efficient, extremely efficient, okay? Let's take a look inside. We're going to slice this impeller open. Remember, it doesn't have a front wear plate. I have to actually cut this impeller open to see what's going on inside. And because it's a small eye, this is a very small eye, very efficient. There's only a small suction location within that eye. And there's very little opportunity for the fluid to recirculate within the impeller back to the suction. So because that eye is so small, it doesn't influence the liquid as much as it's being thrown outward, and it doesn't drive back to the suction as easily. So it's a very efficient, it keeps its efficiency. We don't pump things twice. Whereas a semi-open impeller, 2-vane, very open, less than excellent efficiency. And let's see why. Well, because the suction area is very, very large. That means that that liquid is still being influenced even as it gets further and further out. It's still being influenced by this vacuum generated, and therefore it's always going to have a tendency to recirculate and go back, pump a liquid more than once or twice. Now I did just go back here. I had here small impeller eye, very little opportunity for the fluid to recirculate within the impeller back to suction. Well, that's wrong. That was for the last impeller. This one is large impeller eye, very much opportunity for the fluid to recirculate within the impeller back to the suction. So that's the reason why this type of impeller has very low or relatively low pumping efficiencies. But on the other foot, let's take a look at net positive suction head required. And again, what is that? That is the internal losses of the pump, sorry, the internal pump suction losses. So here we've got a small impeller eye. Yes, Chris?
No, I didn't say anything.
Oh, sorry. So here we've got a small impeller eye. Do you think that's going to be hard to get liquid into that small impeller eye? For sure it is. It's going to induce a lot of losses. It's trying to push 1,000 gallons a minute through a 2-inch pipe. There's going to be a lot of losses in there. So what made this very efficient gives it a very high NPSHR. And in return, the semi-open impeller, 2-vane, very large eye, hey, not very efficient, but that liquid can easily get into the pump. So that's my best way of explaining the somewhat counterintuitive idea that efficiency and NPSHR are kind of opposite in pumps. And this, Chris, is what we were talking about, what I think your question was alluding to here. We have a pump curve and we have a system curve. Obviously, where the pump curve and the system curve, I always harp at this, across is where the pump should operate. And every pump curve should have, represented in some way or another way, some kind of NPSHR, what the losses are going to be within the pump. And I think it makes sense that we can think as we pump more and more fluid out, we're going to get more and more losses within the pump itself, because it's just like a piping system. We're trying to jam more liquid through the suction side. Therefore, the losses are going to increase. Now, there's a little bit of a weird thing on some pumps here. The NPSH does kind of go high again at the lower flows, but then again, there are those NPSH curves that look more like this as well. Either way, once you get past halfway point, that NPSH required, the losses through the pump on the suction side definitely increase with flow. And it makes sense. So let's go back to this calculation. We're still here doing this calculation. Essentially, now we have to take away a safety margin. We'll talk about in a second. And then net positive suction head excess. This is what we want to get to. We want to make sure that after we've taken away all these values, we've still got some pressure, some absolute pressure working on this fluid to keep this fluid. So this is the equation that you'll see. NPSH excess, we always want it to be positive, is equal to net positive suction head available. That's our positive. And then we start subtracting things. The losses within the pump, and then a safety margin. So as long as excess is positive, we are good. We're not going to vaporize that fluid at the eye of the impeller. If it becomes negative, we're in trouble. So again, let's take a look at that NPSH available. If we have a suction filter, I'll ask you, Chris, I can't ask anyone else. If we have a suction filter, will that affect, do you think, or possibly affect the NPSH available on this pump?
So anything that's attached to the suction pipe that's going to increase any kind of restriction, which could increase our friction losses, is going to end up in that calculation as a friction component.
So good. So any valving, anything extra is definitely going to affect that NPSH available. Good. Temperature of the fluid. I'll answer this one, Chris. Temperature of the fluid obviously is going to affect the NPSH because the vapor pressure is built into that NPSH. So if I'm pumping liquid at water at 99 degrees Celsius, well, it's almost flashing already. I don't have to pull too much more vacuum on it to make it boil. Fluid, same idea. I could be pumping quite happily water at 40 degrees Celsius, but I now start pumping gasoline or something a little bit with a higher vapor pressure at the same temperature. That's going to give us some issues as far as the ease of vaporization. And the feed tank right here, the static suction head. Well, if that starts to decrease, then I'm decreasing the amount of pressure I'm keeping on the suction side, on this piece of fluid right here, as it enters the suction of the pump. And finally, if I'm pumping in the Rockies, 2,000–3,000 feet above sea level, my atmospheric pressure is going to drop off as well. So keep that in mind. NPSH available is really the driving positive here. NPSH required. Again, we may have a situation where we've selected a pump at a certain flow rate right here, and that NPSH required seems very, very high. Well, what could we do? We've got a small pump. Well, maybe we need to make another selection. Maybe we need to go and choose a larger pump. Therefore, it's not going to be operating so much on the right-hand side where the NPSH requirement is so large. Essentially, the Qs are the same. I've just picked a larger pump, so that Q is more in the center of the larger pump's operating range. And finally, safety margin. Hydraulic Institute really governs a lot of these things. It's about impeller type and fluid. Low energy impellers, you know, I use low energy impellers all the time. I apply them to water, and we use about 0.6 meters or 2 feet as a safety margin. But it's always good to consult with the distributor or the pump manufacturer. They know their product the best, and they might be able to guide you in, you know, what their idea and their philosophy is on the safety margin. So pump NPSH excess, positive is always a good thing. Negative, you got some tweaking to do. So let's now go through that same calculation again, a little shorter this time. We're not going to go through each one.
Hey, Steph, I think it could be worth answering this question. Go back one slide to the NPSH calculation.
Yeah. And
the question here, when calculating NPSH available,
yes,
should we include the pipe exit into the pump, K equals 1, or is that included in the NPSH required?
The pipe exit into the pump. Very good question. Well, the pump is going to have a flange, and at that flange, and then inside that flange towards the pump, that's all been taken care of. So if, let's say, you have a reducer, increaser coming into the pump, then you definitely have to take that into consideration. But after that flange, you shouldn't have to take anything else into consideration between the flange and the impeller. So no exits. No, or entrance, I guess, exit or entrance. That's all been taken into account in the NPSH-R of the pump. I hope that answered the question. Okay, let's look at a self-priming case or a lift case. What have we got positive here? We've got atmospheric pressure. Great thing, good. It's keeping things positive. Now all of a sudden we don't have a head anymore, a positive head. We have a lift. And this straight away will start taking away from our atmospheric pressure, because we had to draw a vacuum in order to lift that liquid. And that vacuum is a vacuum. It's a partial vacuum. We had to do that. So that's going to be a negative. That's going to be acting on that liquid as it enters the flange, the suction flange of the pump. As always, we have to take away the friction and then the vapor pressure. And then once we have that, we have NPSH. Again, this is the pressure of the liquid, absolute pressure, just as it enters the suction flange, including the vapor pressure. And finally, NPSHR, just from the manufacturer, it's going to change with flow, safety margin. And finally, NPSH excess. We want to make sure that this is positive. Again, if it's not positive, if it's negative, we have an issue. We're going to vaporize this fluid. So we better do something. We better reduce something or increase something so we get more space for that NPSH excess. So again, we want to keep that positive, and if it becomes negative, we're in trouble. So what does this all mean to pumps? Well, if we do start to, we'll go through this, we saw that before. If we do start to vaporize the fluid, what's going to happen? Well, again, we know that we're going to cause a vapor bubble to form, and then it's going to travel into a high pressure zone as it gets thrown out by the impeller. And we're going to see that 2000 PSI pressure spike. So this is what happens. That vapor bubble forms in the eye, and it travels outward and gets pressurized, and we get that collapse, and we get that 200 to 300,000 PSI pressure shock. Not good. And doesn't happen just one at a time. Depending on the situation, we could have obviously millions of these happening at any one time. And this is very, very noisy. And we start to see damage to the impeller right at the eye. Very serious, actually. You can see this one here. Now, the question that's always asked is how long does this take? It's very dependent, but it will happen. It definitely will happen eventually. If you have not enough NPSH excess, you will vaporize that fluid. And this is very noisy. If I had a pump cavitating right here, you wouldn't hear me. Suction cavitation, very noisy, sounds like marbles or stones. But there's another type of cavitation, there's another two actually, and these ones are a little quicker to explain. In order to do this, we need to know about this guy here, Bernoulli. And what Bernoulli said was, as the velocity of a fluid increases, its pressure decreases. And conversely, as the velocity of a fluid decreases, its pressure increases. There's only so much energy in a system, and velocity and pressure, they're always exchanging energy. And if we take a look at a venturi, this is a great example of this Bernoulli's equation or Bernoulli's theory. All a venturi is a pipe that necks down in the middle, okay, and it's hollow. And we're going to take a look at the cross section of this pipe. And if we push, let's say, a certain flow rate through one side, 1 liter per second at a certain velocity and pressure, due to continuity, we know the same flow has to come out the other side. Same velocity, a little less pressure because we've lost some due to friction. But we've necked down the center area here, but we've still got to pass that 1 liter per second. So the only way that we can pass the same amount of fluid through a smaller cross section is the velocity has to increase. And that velocity could increase so much that our pressure could drop. Again, velocity and pressure, they both have energy. And when velocity has to take up more energy, pressure's the bank account for that energy, and it has to pay the price. And we see this all the time in regular life. If we put a paint can, special Bernoulli paint can, below and attach it to a straw, and we attach that straw into that low pressure zone, we're going to have atmospheric pressure pushing on this paint can, and we're going to blow some air across this venturi. We're going to get a low pressure, and therefore atmospheric pressure is going to push that paint into that stream, and we're going to get a paint gun essentially. So this does exist, high velocity, low pressure. Well, what does that have to do with pumps? Well, if we start a pump going and it's pumping 100 gallons a minute, then all of a sudden somebody does this and throttles the valve. Instead of 100 gallons a minute leaving, we're going to have something less. As we know, a centrifugal pump is a variable displacement machine. As we put more back pressure on it, it's going to pump less. Well, unfortunately, that back pressure now means that some of that flow is going to start to recirculate back into the impeller. Okay, once we get past the best efficiency point, we're always going to get this to some extent. But if we really do some heavy throttling here, we're going to start to induce a lot of flow back through the impeller. That doesn't sound like a bad thing until we think that there's still velocity, there's still liquid leaving that impeller. And in between these two streams, these two opposite streams, one going one way, one going the other way of this fluid, there's going to be some turbulence. There's going to be some high velocity. And this velocity could be high enough that the pressure drops and we could vaporize this fluid. And once we vaporize this fluid, that's okay. We've vaporized it under low pressure, but then it might move, and it will move, maybe a millimeter one way into a high pressure zone. And we're going to get that collapsing again, that 200 to 300,000 PSI. And this is called recirculation cavitation. And it's not as noisy as suction cavitation, granted. And where it affects the impeller is, it affects the impeller on the middle to outer side of the impeller vane. And we'll be sending you, obviously, that little achievement award, that award with your name on it with the different impeller zones. And this will be part of that impeller zone that'll show you recirculation cavitation. There's one more type of cavitation, that's called discharge cavitation. And that occurs when we do this. We have a pump running and it's pumping and we completely close the discharge down. Now what that induces is recirculation cavitation for sure, that will definitely take place. But it also induces this discharge cavitation. And what that is it occurs right here at what we call the cutwater, where this liquid is leaving the impeller vane. Let me get really close here so we can see. We start to get this recirculation taking place between the cutwater of the volute itself, of the case, and the impeller vane. And as this impeller vane comes around, it squeezes and makes this area between the cutwater and the impeller vane really, really small. And guess what happens when we have a small area with a lot of flow traveling through it? We get some high velocities. And with high velocities, we're going to get low pressure. And we vaporize this fluid right there. That fluid is going to vaporize. And then what happens is the next impeller vane comes around and pressurizes it. And therefore, we're going to get that 200,000 PSI vapor bubble collapsing back into liquid again. And that affects the tips of the impeller vane. And you'll see this again on that impeller that we're going to send to you. And also, it's going to affect that cutwater case area. Now, this isn't very noisy again. Suction cavitation is definitely pretty well always the noisiest kind of cavitation. But my question is, what's worse? And I'll open this up. What's worse for the pump, suction cavitation or this recirculation discharge cavitation? And I'll let you answer that. I'll give you 10 or 20 seconds here to answer that. And we'll send you a Tim Hortons card.
We got some answers. Yeah, we got some answers coming in.
Yeah.
And they're all over the map. They are probably, I'd say more people are saying suction. Others have said the other two, but more people are saying suction.
So we get to keep some of these cards for ourselves.
We do, yes.
Okay, suction cavitation, let's look at it because it is noisier. And that is definitely, you would think for sure, if you're listening to a pump suction cavitate, you think yes, but it isn't. Suction cavitation affects the eye, the impeller eye. Remember, recirculation and discharge cavitation affect the outer portions. So let's see how that affects the impeller rotating body itself. So all these suction cavitation blasts that are happening as this vapor bubble collapses and we're getting 200 to 300,000 PSI pressure spikes are all happening down the shaft itself. That's not great for the bearings. It's not great for the mechanical seal. But what's worse is if these blasts, these 200 to 300,000 PSI pressure spikes are acting here, right here, radially, because every time that impeller vane passes that cutwater, we're getting a bang, a bang, a bang, and eventually we will fatigue that shaft off. Sorry, that impeller off the shaft. We're going to break that shaft. So again, the noise, definitely suction cavitation, but discharge cavitation will definitely break shafts. And here's one right here. So, you know, if we ever get sent this, we want to solve your problem. And what we'll do is we'll also ask for the impeller so we can take a look at if we can see some discharge cavitation on the impeller, and always suction and discharge gauges always help as well. So how to avoid pump cavitation? Well, let's give away some cards here. Let's see if we can do that. Let's stay within the operating range. So remember recirculation cavitation. I'm going to open this up here. Where does recirculation cavitation take place on the pump curve? Is it in location 1, where the NPSH is very high, or is it in location 2, where the pressure is very high? And I'll give you a couple of seconds here to think about that. Okay.
Yeah, we are, I'd say 80% of the people have said 2.
Good. And that's the case. We've got a very high pressure, low flow. So we're getting that internal recirculation from the discharge back into the pump impeller. Good. What about discharge cavitation? Does it occur where our NPSH line is very high? Does it occur where we're running very, very slowly? Or does it occur in location 2, where we have high pressures, low flows?
Yep, got some answers coming in.
Okay.
And we've got, yep, up into the 30-odd people, and yep, 2, answer 2 is correct.
Answer 2 is correct. Now I'd like to lay a bet. I'd like to lay whatever cards people have won today on the next question. Where does suction cavitation take place? Location 1, where the NPSH is very high. Remember that. That's something that's going to take away from that excess. Location 2, or don't know. What do you think the answer is there? Suction cavitation.
Yep, got some coming in.
Okay.
And looking like 1 is the consensus.
What good. So we're going to get all our cards back. Because I agree, 1 is definitely a good chance of it. But 1 only represents, over here, it only represents the NPSH. I can still suction cavitate right here where my NPSH available, when my NPSH is very low, if I block the suction or I start pumping gasoline at high temperatures. So I agree that this is a tendency that suction cavitation will occur over here, but not necessarily. Suction cavitation can occur anywhere along the line, whereas the other 2 cavitations cannot. They will be pinned to the top left-hand side.
We did get a couple of answers. Trick question. Good call.
Okay, good. Okay. And what does it all come down to? Hey, pumps are important, but I always think system curves are more important, because without a good system curve, you don't know where this pump is operating. You could be operating on the left-hand side, in the middle, or over to the corner. You can buy the most expensive pump in the world, but if you don't have a good system hydraulics understanding, you're just throwing your money away. So what we're going to give you in a day or 2, we'll send you an email. We're going to give you this curve that shows you, embedded into this little certificate, that shows you the locations of bad zones on the pump curve. Green is recirculation, red is discharge cavitation, and then the blue zone. And the blue zones happen in the eye, the green zones happen in the outer, and the red zones happen on the tips of the impeller. And again, notice the suction, there's no blue on the curve, because I cannot guarantee that that's going to happen on the right-hand side. So you're going to get that, and it's going to be personalized. Now I'd like to just get out of this for a second here, and I want to show you something, because it was locking up my computer before. So if it locks up the computer now, no biggie. What we'll also send you is going to be this PowerPoint slide, and it's pretty cool. Can you still see this, Chris?
Yes, we can.
And what you're going to get is you're going to get this little model here that you can do this with, and it's going to show you the blue sections for the suction cavitation, the green sections for the recirculation, and the red section for the discharge. So if you're bored at work and you just want to open this up and fling it around, that's fine. And it's kind of cool. I'm going to work on a few different types of impellers and do this to them, because different impeller styles cavitate in different locations. And just in case you want to know where it came from, there's John Brooks at the back, just in case. So that's pretty well it today. We've kind of ran out of time. I really want to talk about series pumping, but we ran out of time. A few people did ask about that, and we didn't cover that in the second webinar. We don't have a lot of time here. Chris, do you have any questions?
There's a couple of questions. Now, Mitchell says, operationally, what causes recirculation and discharge cavitation? And then he says, operating below MCSF. Now, I might be having a Thursday afternoon meltdown. I'm not sure I know what MCSF stands for.
MCSF.
But operationally, what causes recirc and discharge cavitation? So, you know, you could be looking at, if the pump was if I understand the question, minimum continuous safe flow.
Okay. You can answer it, Chris, if you want, on that one.
So operationally could be a number of things. If the pump was fine when it was started up, obviously you could end up in a accidentally closed valve situation. You could end up where the discharge piping has perhaps scaled over time, and maybe is forcing the pump to run a little bit left on its curve than it did originally. Running below the minimum, running below that minimum continuous safe flow, you are starting to push the duty point, you know, towards the left-hand side of that pump curve. So you could end up, as Steph's got there on the screen, you've got an operating range. So this happens to be a Gorman Rupp. Gorman Rupp advertise their operating windows in this fashion. The further you get towards the left of that operating range left line, and then beyond that, further towards zero flow, then you're going to start getting into recirculation cavitation will begin, and then eventually you'd get into discharge cavitation as well towards that zero flow. Hopefully that answered that question.
And just to add, do you think if you had a 6-inch pump, nominally, maybe you should be using a 4-inch pump, a little smaller pump that can operate into those lower flows area? Maybe you got the wrong pump.
Two more easy ones. Do you have a spreadsheet to calculate NPSH?
Yes. Anyone who wants to email me, you can. And yes, for sure, we can definitely send you a spreadsheet for sure. And I'll just put my email address up here, right here. And
there's one more. It's quite interesting. This has come up. Controversial type question. It could be a good one to end. Thank you for this one. What is cavitational resistant material like stainless steel impeller?
Oh my goodness, that's really good. Cavitational resistant, you correct me if I'm wrong, Chris, but stainless steels are many times thought of as being cavitationally resistant because they're more malleable. It tends to gall when it's hit by that 200,000 to 300,000 PSI. So we don't see the cratering effect on the actual piece of, on the impeller or the volute. We see a more galled or a plasticine kind of a smooth hit. And so it doesn't look as bad. But the forces are still going to be the same. And those forces are still acting on the bearings, on the mechanical seal, on the shaft. So eventually, it doesn't make a difference what you made the actual material that's taking the impact. Your whole drivetrain is taking the abuse. So
it's remembering what you said, that the cavitation is a system related issue, not a mechanical related issue, and that, you know, cast iron, ductile iron tends to look like the crater of the moon, whereas stainlesses tend to look more like plasticine.
That's correct. That's correct. Gee, I think we ran out of time here.
Yeah, that's that. Yeah.
Well, what we'll do, guys, is we'll look at those answers, and then we'll send out definitely some of these Tim Hortons cards, and we'll definitely be sending out that little achievement award, definitely printed off. It's a nice little reference, and also then the electronic impeller that you can play around with and take a look where the cavitation occurs.
We have an interesting comment before we leave. That's like thinking a flexible coupling will allow for more misalignment.
That's a great one. I like that.
Thanks,
one. We've heard that.
All right. Well, thank you everybody for attending, and links to this presentation and the other ones that Steph and Chris have put on will be sent out to you. And also watch for our invite and registration information for the next seminar on May 28th. And Steph, it's on PD pumps, right? On positive displacement pumps?
Positive displacement pumps, yes.
Perfect. That'll be coming out soon as well. And again, thank you everybody for attending. We really appreciate it and for your time and interest, and look forward to seeing you in a couple of weeks.
Thank you.
Thanks a lot.